Good morning, everyone. Welcome to the Bangalore Series Seminar. Today, I have the pleasure of introducing the speaker, Karthik CS. Karthik did his master's from Normal Superior and his PhD from Weizmann Institute of Science, and followed this up with postdocs at Tel Aviv University and New York University. Since 2021, he has joined as an assistant professor at the Rutgers University. His research interests include complexity theory and discrete geometry, an emphasis on hardness of approximation, fine-grained complexity, and parameterized complexity. Today, he has agreed to give a talk on the hardness of approximation of diameter clustering. So, without much further ado, I hand it to Karthik.
Thanks. Today I'll talk about something that was some recent work with a bunch of summer students. So this is a clustering objective which is studied in the 80s for max K diameter. We're going to study it in the setting when the number of clusters is small, like 3. So let me say that this joint work with just be informal and use first names. So these two are undergrads and these two are master students, various places. They came in the summer and we worked on this. So let's start with clustering. So clustering can be broadly considered as the task of partitioning some input data into parts such that each part has some property that's kind of good. And so then we can try to formalize this. So when we try to formalize it, that we have some metric space gamma. And our input is typically some subset of the metric space. And on top of that, we are possibly given the number of clusters that we want. Okay. And our output, some partitioning of X into X1 such that this partition is good. Now, what does it mean to be good? Well, if you're looking at the k-means objective, then you want to minimize the sum over all clusters. And within each cluster, you have basically sum of all p comma q in xi, the distance of p and q square divided by the size of xi. You probably would have seen it in the center-based version, where you want to pick a center and minimize the sum of distances square to the closest center, you pick a center. But in the Euclidean metric, for instance, it would be something of this kind. So let me put this is this is the Euclidean metric. I can write it in this form by looking at the variance. So what I want is to look at each cluster, look at all pairwise distances, square them, divide it, normalize it by the size of the cluster, and sum this over all clusters.
What is this indicate?
if there is no square, then I think it's average distance between any two.
Yes, so it's no square, then it becomes what is called a min-sum objective. The reason there is square is because of Gaussian structure. So each cluster is optimized when it's a sphere. So if you want spherical nature, you want it to be square in Euclidean norm. And if you don't care about that, you can ask what is the minimum of, for instance, this is what we just suggested. This is called the min-sum objective. On pairwise distances without in the cluster. And again, these are all classic things. It's all a question of modeling. So you, as a person who wants to do a clustering task, is going to model what is my objective to minimize. These are some popular natural choices to take. One other choice which I want to mention before I go to diameter is case center, where you want to minimize the max size enclosing bond of xi. So you look at your k parts. For each one, you find an enclosing ball, and you think of the radius of that enclosing ball. You take the maximum across the k parts. You want to minimize this. This is called the k center. Like, what is the ball radius? I need to capture all the k things. And what we are interested in is k diameter. Which is minimize the max distance. Look at each cluster and you look at the diameter of it, and you want to minimize the maximum diameter. The farthest pair within the cluster. So for every cluster, look at the farthest pair and take the maximum across the k clusters. That's the cost of your clustering. No, because they're related. The radius is different. It's a factor square root 2 in the Euclidean metric and a factor 2 in general metrics. Yeah, and min-sum we don't normalize. So this is like the 4 objectives, and I'm going to focus on the diameter. All of these are studied 60s, 70s, 80s. Notice the difference is that these are min-sum objectives because they're summing over things, and these are max objectives. So whenever you have a max objective, it becomes easy to understand it. I'm not saying it becomes easy to track, making it efficient or something. In the sense that your algorithmic tools, they don't need to be very sophisticated. Your hardness tools don't need to be very sophisticated because it's a max objective. So greedy approaches, these kinds of things typically work. So we end up understanding these things significantly faster as a group than this. Yes. In k center, for instance, so if I have suppose I had this, and I want to cluster it into 2 parts. So I would naturally choose this cluster. Right? Now look at the diameter. So for the k center, you need to trap them in a ball. So this would be this ball here, containing these 3 things. And for this, it would be this ball. Right? And then you ask, what is the radius of these balls? For this, it would be from here to whatever this thing is. From here again, it would be the radius between these things. But for the diameter, you look at the cluster and you look at the farthest pair. Okay. And notice that the farthest pair and this can be off by a factor of 2.
The clusters change in this case.
In
When we go to K diameter. So
yeah, so if you want square root, you're okay with the square root 2 approximation in Euclidean or a 2 approximation in general metrics, you can take the clustering from the K center and it carries over with that factor approximation. But it can, if you want exact, it can change. You take the min over all partitions. So this is the min over all partitions. This is the max over all clusters. Is this fine? So any questions so far?
okay, once again, why the first objective is a natural one?
The first one?
Yeah.
The first one, let me say it in a different way, the same objective. Which is you are given K, you're given a point set. You want to find K points. Let's say they might be in the point set, not in the point set, doesn't matter. Such that for every point in your point set, you map it to one of the K points, which is closest. Okay. And now what you want to minimize is the sum of distance square to the center it's going to. This is a natural thing, right? Because you're trying to minimize, in some sense, the variance of each cluster. And so that version I told has what is called the median, the mean. So now the mean itself can be written as the sum on all coordinates divided by the size of the cluster. So when you write it in that form, the expression you end up getting is this, because this doesn't have a mean. The mean is incorporated into the thing. So this thing is coming here to normalize the size of the cluster that's there. Because think of a million points very tightly packed versus 3 points far apart. They might have the same objective. Clustering objective value might be the same thing. Just because here you have mass and here you have distance. So you want to balance between the two things. So far we are good. So what do we know for K diameter? So in K diameter, your input is some X and some K. Your output is a partition. And you want to minimize the max diameter. Right? Now, there are several parameters here of interest. Let me say the 3 parameters of interest. One is the metric space. So we can think of general metric, LP metrics, edit metric, and so on and so forth. So for instance, general, when I've just specified all pairwise distances and they satisfy triangle inequality, or L1, L infinity, L1, L0, L2, so on. And if we are in LP metric spaces, there is another interesting thing, which is dimension. Low dimensional spaces might be more easy to come up with algorithms versus high dimensional spaces, because there are separators in low dimensional spaces which don't exist in high dimensional spaces. The third, K is K fixed, like 2. Is it linear in the input size? So there are 3 parameters of interest. And in some sense, a good understanding of the approximability of a clustering objective means you have understood all possible combinations here. Okay. And it turns out in the 80s, we did understand many combinations. This is the 80s. So we know from algorithmic side, there's a 2 approximation in polynomials. This is basically Gonzalez. That's correct. So if you're given the diameter to be some alpha, then you can output a partitioning whose diameter cost is 2 alpha in polytime. Yeah, if you can guess what the diameter cost is, and for each guess by just sequentially increasing the powers of 2 or something, and you can get a 2 approximation. This is for all metrics. So really the question then is, can we beat this 2 approximation by utilizing either in all metrics or by using some special structure of the metric? So this turns to hardness. So in general metrics, this is not possible. Again, this is from this 86. I think correct limit is not far. And then, so we can then ask for L infinity. But even for L infinity, what do we know from that? I mean, you can just take this instance and embed it using what is called a Frechet embedding, and you get 2 minus epsilon hardness. And this is true for L2. So using some slightly more non-trivial techniques, we can get 2 minus epsilon for L1 and L infinity as well. And this is moreover true in the plane. When the dimension is 1, the problem is in P. So 2 is the most natural place to look at something non-trivial. And it becomes that it's NP hard to even approximate better than something better than 2. So this is due to Federer P. And for L2, it is 1.969. So this gap of between 1.969 and 2 is open for like 40 years now almost. That's not the focus of this talk, but it's clearly this is like one of the more major open problems today. Just to bridge this gap, either come up with something better than 2 if you're from an algorithmic side, or 2 minus epsilon from a hardness side. Right. So all of these hardness results hold when k is part of the input, typically linear in the number of points. So each of your cluster size is like 2 or 3. That's the title of the talk.
Oh, okay.
Oh, right. So a few clusters. So one of the main things we are looking at is what about and now necessarily the dimension has to be high, because if the dimension is fixed and k is fixed, the problem is in P. So what about fixed k when the dimension is high? And it turns out that k equal to 2 why? How many partitions are there of n points into k parts? It's k to the n, not n to the k.
P, but when k is fixed and potential like
And d is fixed.
P.
Is
I think this algorithm like do approximability for all the things. That is for all.
yeah, that doesn't care about, you just give me all pairwise distances. Yeah, I mean the idea is very simple, right? Like you take a point, you take its farthest point, you take its farthest point from this place. You do this k times. You have k centers, and now map every point to the closest of these k things. You get a partition, and you can argue that this is, to approx. The standard greedy stuff. Yeah.
2 points. I mean the metric itself. You know the distance in constant distance or other but
Sure.
the dimension is high. Will that also not take 2?
The dimension is n. Then we're fine. Right? Yeah. And in Euclidean metric, it doesn't matter how high the dimension is because you can do JL and bring it down to log n. Okay, so why is this in P? Do you see it? In fact, this is very instructive because general observation, k diam reduces to k color graphs. So what is the proof of this? You're given n points, and either you have that so let's guess the optimum diameter cost. Let's call it alpha. Now these endpoints become n vertices, and you put an edge between two of them if their distance is more than alpha. Okay. Now, so you have a graph. Assume this graph was k colorable. Then you get a k partitioning of your point set, such that every pair of points within the same part don't have an edge, or their distance is at most alpha. On the other hand, if you had a partitioning such that the diameter is at most alpha into k parts, that gives you a k coloring. So this reduction gives us that two diameter reduces to 2 coloring, which is just by bipartiteness checking. So it's in P. So the next natural question is, what about as a side remark? K equals to K diameter is NP, but remember the K center problem, which looks very similar. That's NP hard. So for K equals to 2. So it sort of differentiates the two problems, finding the radius versus diameter. So next we can ask, what about K equals to 3? You take whichever problem you want. K means K median, and define these. K center. All of them have a p task for 6K. So your first hunch would be K diameter also has a p task. Because when K is fixed, suppose we can solve essentially all the popular clustering objectives, we can get a p task. So you would guess that why should this problem be any different? It should also have a p task. Turns out the answer is no. We can prove strong NP hardness results. So what is the result?
Interesting, right? So for K is equal to 2, K diameter is in P, but K center is in P hard.
Right.
So for N is equal to 3, K center has a P task.
Right. Somehow. Yeah. So this reduction does not give you hardness because you're reducing from the problem you want to prove is hard to K coloring. But what we will see is that there is a very complicated reduction, the reverse direction, morally speaking. It's not exactly this. So hardness of 3 coloring will translate to diameter. So that's these are sort of very interrelated things. So I'm going to draw the let's do the metric. We have general metric. So all of this is K equals to 3. So general metric, L infinity. Yeah, but even go into general. Let me just use L infinity. L1, L2. Whatever results I'll write for L1 also hold for Hamming L0. And let me write here hardness. So it turns out for L infinity and this you can get 2 approx. For L2 Euclidean, we can actually do something smart. You get square root 2, which is like 1.414. The idea is just simple. So this is not us. Who's this? It's the people who came up with the p-task for K center. They came up with a p-task for K center when K is fixed. And there's a simple theorem called Jung's theorem, which is that if you give me the radius, the diameter cannot be at more than square root 2 factor away in Euclidean metric. So that uses, and we can use that and get a 1 plus epsilon times square root 2. We get this for K diameter. So now the hardness. So implicitly, this was known. This is from Megiddo, 90. And they're not directly written in this way, but the proof more or less goes through. So really the question is here, L1 and L2, what is happening? Because these are highly structured metrics, so you can do something very non-trivial. Our result is that 1.5 here.
So this figure, A means A begins less than graph beta. That's for any metric. It's
As far as I remember, yeah. Let's say I'm 99% sure. I'm 100% sure. So you can see that if I get an instance of hardness for L1, and it's in Hamming metric, so it's all 0, 1 vectors. Square root of that already implies for L2, because the distances get square root compressed. So that you get square root 1.5, which is like 1.2-ish something. For L2, yeah, you can come up with something even more non-trivial. And you'll see the techniques involved become surprisingly sophisticated, which is not expected, because these problems usually, it's the simplest algorithms and the simplest ideas that give the right answer. And here it's not even close to the right answer, and it's already quite messy. Any questions right now? I want to start by showing the reverse direction for L infinity. So you will see why coloring is the right problem to study. And then I'll start to build up. So the roadmap for now is the following. First, for the L infinity result, which is 2. And second, show L1, but 5/4 hardness, not 3.5. Third, show L1 3.5, which I don't know how much I can show, but to some extent. Then fourth will show L2. If I have some time, I will tell what are the bottlenecks to improve this further. It's related to some long-standing questions in extremal graph theory. It's L infinity. We are doing reduction from 3 coloring to 3 diamond. In other words, we are given a graph G. Then end up building a point set P. Okay. It's going to be the size. There's a 1-to-1 correspondence between the vertices of the graph and the point set we'll build. And it's going to be in E dimensions, where E is the number of edges we have. So we build a map rho from V to E. P is just formals. So how will we do this? The first trick is to arbitrarily orient the edges of the graph. It doesn't matter what, but arbitrarily orient. Now we have oriented the edges. I haven't defined what row is, right? I have to define what it is. Show it's polyton constructible, it has the properties we want, and so on. So arbitrarily orient the edges of the graph. And now I want to tell what the eth coordinate of a vertex V is. The eth coordinate is one of three things. So it's going to be +1, -1, or 0. It's +1 if E is incoming to the vertex V. It's an incoming edge. -1 if E is outgoing from a vertex V. And 0 otherwise. In other words, if E doesn't touch V. And this now it completes the reduction construction. So now we have to analyze this reduction. So suppose there was a 3 coloring. That means there's a partition of V to from V1, V2, V3, such that each Vi is an independent set. Now take some 2 vertices. Actually, before take some 2 vertices. Let me do this. Take some 2 vertices in Vi, U and V. Okay, and let's look at their eth coordinate for some E. Clearly, there is no E such that U and V are both touching it, because that would mean UV is an edge, which would contradict the fact that Vi is an independent set. So for every pair of vertices within the same independent set, on every coordinate, only one of them can be non-zero. Right? So their distance on any coordinate can be at most 1. So we know that for all U, V belonging to Vi, the rho of V minus rho of U L infinity norm. In other words, the diameter cost is at most 1. Now, soundness, I won't write down, but let's see it quickly what it is. In soundness, suppose we had a partitioning of P into P1, P2, P3, such that every pair of points within the same thing is a distance less than 2. Now, notice from our construction that the distance between any pair of points is either 0, 1, or 2. So if the distance is less than 2, it must be 1. So we have 3 parts of the point set, and in each part, the diameter is at most 1. That means that those 2 pairs of points correspond to a non-edge in the graph, because if they were an edge, their distance would be 2. Hence, we get that 1 versus 2 minus epsilon is NP hard for 3 diameter and infinity metric. Any questions? Yeah, so let me say the same thing in a different order. For any pair of points, any pair of vertices, if they have an edge, let's say the edge is E, on that coordinate, one of them will be +1, the other one will be -1. So their distance is 2. At the same time, for any pair of vertices, if they don't have an edge, their distance is 1. So we have this property of our rho. Well, it cannot be 0 because there is, if you assume that there is no isolated vertices, because everyone has some edge. So that's fine, right? So now once we have this, the coloring proof is easy. Because if you had a 3 coloring, the diameter is at most 1, because you have 3 independent sets and every pair of vertices is a distance exactly 1. And on the other hand, if we had a partitioning of the point set into 3 parts, such that every pair of them distance is at most, say, 1.99, we know that there is no such thing as 1.99. So the distance has to be 1. And hence, it means that every pair of them correspond to vertices which don't have an edge. So we found partitioning into 3 independent sets. So this is the vanilla reduction which we have built on. So this reduction here is inspired by a technique from Trevisan. So inspired. We show that 3 diameter L1 it's hard to approximate. (5)4 minus epsilon plus.
Distinguishing between 1 and 2 minus epsilon is infinity.
But for L infinity metric. Yeah, so that's this proof. Some variation of this or some version of this appeared in Megiddo. So we're going to show this now. So to any of these proofs, there are 2 parts. One is the starting assumption, which will be some coloring with extra properties. So we'll have to guess what properties they are, and they still have to be NP-hard. Second is the embedding, which here was some naive thing, but it can get very complicated. So there are 2 components to any reduction in this framework here. So here for the showing 5/4, we need a stronger 3 coloring guarantee. What is the version we'll use? We will use that 3 coloring, 4 regular, 4 edge colorable. Graphs is NP-hard. So 3 coloring on not only 4 regular, but 4 edge colorable. In other words, if you only consider the class of those graphs where you can give a color to each edge such that using only 4 colors, such that no 2 edges which have a common vertex have the same color. And 3 coloring the vertices of that graph is NP-hard. So this is our starting point. We will do the same old thing here, except our row. So we are given a graph G. We'll build a pointset field. Except our row is going to be something like this. I need to start saying something here. Are everyone familiar with Hadamard codes? I can briefly tell what they are. I think I need that for the construction process. So Hadamard codes are constructed as follows. This is the all ones matrix, and where H1 is so it grows exponentially. So H1 is a 2 cross 2 matrix. H2 is going to be a 4 cross 4 matrix. H3 is going to be a 8 cross 8 matrix. So Hn is a 2 to the n cross 2 to the n matrix. Now you look at the rows or columns, doesn't matter what, because it's symmetric. So and then those are the vectors that we are interested in. So you're interested in 2 to the n vectors in 2 to the n dimensional space. I'm going to think of 2 to the n as n. So you're interested in n vectors in n dimensional space. What the properties you get from this is that there is the zero vector, but if you leave that out, all other vectors have n over 2 ones and n over 2 zeros. And at the same time, if you take any two vectors, it forms a linear space, linear subspace. So if you take any pair of vectors and you subtract them, the difference is also another column in this thing. So the difference between any two vectors is going to be of distance n over 2. This is if this is too messy to think of, you can think of random strings.
When subtract two vectors, something big.
You are over F2. So you can think of random strings. So instead of subtracting, that's why let's say agreeing and disagreeing. So every pair of columns or rows agree on half the coordinates and disagree on half the coordinates. And if you take, so this holds for true. And in general, if you take any vector, there's half of them are ones, half of them are zero. Now, instead of thinking of Hadamard, you can think of random strings. If you randomly sample each coordinate to be 0 or 1, you'll roughly have n over 2 ones and n over 2 zeros. So take a n-bit vector uniformly at random. It will roughly have half ones and half zeros. In fact, the standard deviation is going to be about square root n, order square root n. And moreover, if you take sample n many random vectors and you measure every pair of them the distance, with high probability, it's going to be n over 2 plus or minus little order terms. So this is like some concrete version of de-randomizing it with very strong distance properties. But even the random vectors is enough. Okay. So now that I've told this, I'm going to now define what the row is. The edge set is 4 edge colorable. So in other words, I can decompose the edge set into 4 parts so that these are 4 matchings. So from this part, we know that E can be written as M1, M2, M3, M4. So you have 4 matchings whose union is the edge set. What we will really do is for every vertex and every matching, I'm going to define its embedding. And then the final embedding of that vertex is just the concatenation of the 4 embeddings that we have. So it will become 4 times its length. Yeah, is this fine? Right, but for the NP hardness proof, you just need to show there exists. Oh, you mean here? Here. Yeah, here we know. Yeah. It's yeah. Yeah. I mean, if it's a 4 regular graph, it is 4 edge colorable. You can find it in poly. So let's look at some matching MI. This is going to be for every vertex, you'll have something like this. Right. So intuitively, we think of it as follows. The number of coordinates we have is going to be the number of edges here. So let's say this was some E1 up to some EP. This is the matching MI. Then the vertex B is going to have some amount of coordinates, which I'm going to specify. But the idea is the following. I will associate to this a random string. Okay. And then I will flip all the bits and associate that string to this. So this vertex gets some random string R1. And this one gets 1 minus R1. For this, I associate R2, and this gets 1 minus R2. And so on. So this gets RT, 1 minus RT. If a vertex does not participate in the matching, then just give it all zeros. Doesn't matter. So we have done this. So
Okay, the vertex part.
doesn't need to be a perfect. I mean, maybe here it is, but in general,
Here, like every
here everyone does, yes. But this technique is in general true for. So what you do is for each matching, I have an embedding of a vertex to some random string. Now let me label this as R1I because it's in the ith matching. So on. Now for a vertex B, it's going to be some vertex in each of those 4 matchings. Just concatenate all of them. So I'm going to abuse notation and write it as vertex V is just going to be RV1 concatenated with RV2, RV3, RV4. Okay. What is the properties we have? Suppose U comma V is not an edge. The graph. That means
This is a body length with random string.
let's say n length random string. Well, log n even suffices here, but let me use n just to be safe. It's going to be 4n. And 4n over 2 or something like that. Yeah. We'll have just n over 2 things, random strings I'm sampling.
So that's what body is.
Mod what?
Like the number of edges is also linear. 4 edges.
Yeah, so it should be something like this. I don't care as long as it's some order which is linear in there. Now take any pair of vertices which don't have an edge. So in other words, in every matching, they will be somewhat different. So they will get different random strings. Now we know that the distance between any 2 random strings is roughly half. Right? So on each of these 4 parts, their contribution is going to be half. So I can write up to normalization that then rho of V minus rho of U. And again, up to normalization is 4 times half. Because they agree on half of the things and disagree on half. On the other hand, suppose then there exists a matching in which there'll be exactly the opposite endpoints. There, their distance is going to be 1. And on the remaining 3 matchings, they'll pay half. So there I can write rho of V t times half plus 1. And this ratio is 5/4. So now you do the classic thing we did from coloring. In the S case, there is a 3 coloring. So you have 3 independent sets. So every pair of vertices don't have an edge. So the diameter is 2. In the no case, you give me any pair of any diameter clustering whose cost is less than 2.5. But I know the cost is less than 2.5 means it has to be 2 because the distances are multiples of these things. And hence I can go back and construct a 3-color. So this is for 5/4. Can use the colors now. Yes, I have really no hope of explaining. So this is the starting of the work where we reach now. I'm going to draw what is called the Wattal graph. So 1970. Wattal came up with the smallest graph, which is triangle free, which is 4 edge colorable and 4 vertex colorable. Okay, it's a graph which looks like this. And in that graph, if you remove any edge, it becomes uniquely 3 colorable. Because it's the smallest graph which is 4 colorable. So if you remove an edge, it becomes uniquely 3 colorable. Because if it's not uniquely 3 colorable after removing an edge, it's like there are multiple colorings. Then you can, when you add an edge back, it won't be 4 colorable, it will remain 3 colorable. So the graph looks like this. So everyone is connected to its diametrically opposite. And to its adjacent. This is uniquely 3 colorable because I'm going to remove an edge. You can verify it. So it's this graph. Okay. So why is this useful? What we'll do is the following. We will take our starting instance is going to be 3 coloring on cut edge free. Three regular graphs. Then we will look at its incidence graph. So it's a 3 regular graph. So now look at the graph where every edge is a vertex. And here notice that every 3 edges incident on a vertex, right? So you put a hyper edge on it. So what you end up getting is a hypergraph where the number of vertices is the number of edges here. And you have hyper edges. So the degree is 2 because every vertex has 2 uniform hyper edges on it. Okay. And then we will replace the edges, the hyper edges there with this gadget. Why? In this gadget, if I introduce this edge and connecting all the this one, these three endpoints are from the hard instance where they had a hyper edge between them. We remove that hyper edge and we still introduce these edges. These three endpoints are uniquely three colorable. Okay. So it turns out that now what we have built up this graph, if you are giving me a three coloring for the original thing, once I fix the three colors here, all of these colors are uniquely fixed. So this problem remains NP complete for graphs of this structure. Why is this interesting? Because we can use what is called quadratic codes, which you can think of as pairs of random strings, to embed this graph now. So this is just a part of the graph, right? So there are so many other things. We can embed this graph such that every pair of vertices which don't have an edge are at distance 1, and every pair that is having an edge are at distance 3/2. The embedding is quite involved, so I won't go into that. And so this gives you the 3/2 for L1. Okay, now let me draw another picture to show how to get the 1.304, which is better than square root 3/2 for L2. This is a 3D image. I'm going to try drawing it in 3D. So we have a sphere, unit sphere. So imagine the three circles that are there defining it. So you have, for instance, this one. You have this one. Right? And then you have this one in the surface of the board. Now let's define three regions, which is this region here, this region here, and the back region. These are three regions of the sphere out of the 8. You're talking about the surface or the surface, just the surface. So there are 8 patches of equal isomorphic shapes. And we took the 3 ones. Notice they are connected at a point, like these two meet here, these two meet here, these two meet here, and sort of unique point connections. And what we will do is that let's call this EA. Then this is negation in here. Like there's the unit sphere, right? So let's call this EP. So this is negation EP. This is EC. So this is negation EC. Now, if you normalize the sphere by square root 2, you will get that this is one cluster, this is one cluster, and this is one cluster. The diameter is 1. After normalizing, it's true, Chandra. If you normalize it by square root 2. On the other hand, you get the stronger property that if you have a clustering of this point set, let's say that we have taken a epsilon neck here, and here. So you have this point set. In the yes case, I can cluster this into 1, this into 1, and this into 1, and I get the diameter is at most 1. But now take any clustering of this into 3 parts, such that the diameter is at most 1.304. So 1.304 is actually a rather intuitive number. It's 1 plus 1 over square root 2 the whole square root. This distance, it comes up in a calculation, which we'll see now. But if you cluster this into any three parts, such that the diameter is at most this, then you have that EA, EB, and EC are in different clusters. This is structural theorem. That any clustering where the diameter is less than 1.304, these three endpoints end up in different clusters. These three endpoints play the exact same role as these three free things here. So then I can take a hard instance and embed this gadget instead of an edge. And they would play the same role. So the proof goes through by giving 1.304. So why is it 1.304? Assume for a minute that there is some clustering of this point set into three parts, such that EA and EB are in the same cluster. Okay. But at the same time, the diameter is at most 1.304. What you will get is the following. So look at these midpoints here. These are the dangerous midpoints. And if EA and EB are in the same cluster, then either this is in that cluster or this is in that cluster. And if this is in the cluster, this distance is large. This in the cluster, this distance is large. That means that both of them are not in this cluster. But if both of them are not in the cluster, look at EC. Its distance to them is large. So you will get that and this distance, if this distance was 1 normalized, that distance is exactly this 1 plus 1 plus 1. So that's the high level idea of how you get 1.304. And yeah, there are more details, but what you get here is that if you want to improve this hardness result, you want to say that whatever gadget we use here, if you look at, so this is a point set, right? You can think of its corresponding graph, where you put a vertex for every point and an edge if the distance is more than 1.304. This graph needs to be three colorable, but have no large odd cycle. So the odd cycles in such a graph needs to be of unbounded length. They can't be small because that would contradict many things. So we would want the gadget to have properties, whatever it is, to get the square root 2 hardness, such that the graph it correspondingly builds is three colorable, but has no bounded odd cycle. And these are open problems that people have been studying in the graph theory community for 70s. And so, yeah, so it sort of connects these things. Large odd cycles. So it's this we don't know very well yet. So explicit constructions, it's still open, like people are still constructing. Yeah, I mean, I think it's square root 2 is possibly tight, but there is no real reason for me to believe. Well, if you get 2 for in L1, which might be true, it immediately implies square root 2. So that's one reason, and I believe 2 might be true for L1. That's why I believe square root 2 is tight for that. But it's one of the first instances where we get a stronger Euclidean, like we have used typically in hardness of clustering. You can't use the Euclidean property to get stronger hardness. But here we could. Like there are geometric ideas which you can't mimic in L1. So this is sort of uncommon. That's it. Oh, thanks. Thanks. Thanks.
it.